Hello everyone, I am Dikshit Hegde and today I will be presenting LGAffordNet, a local geometry aware affordance detection network for 3D point clouds. This work is carried out along with Ramesh Ashoktabir and Uma Mudengudi from the Center of Excellence in Visual Intelligence at Kerala Technological University, India. Affordance refers to the possible action that can be performed on an object. For example, if a door has a plate, the affordance is to push it. However, if the door has a handle, it introduces ambiguity whether to push it or pull it. Let us consider an image of a chair. The sitting area affordance is highlighted, but there is uncertainty about the comfort of the sitting area. To better understand the scenario, we use 3D point clouds which has additional information of the scene. Recent research focuses on segmenting the parts and interpreting them as affordance. However, these approach often lack information about the confidence level of the sitting probability. To address this issue, a data set, namely 3D Affordance Net data, was introduced at CVPA 2021. This data includes partnet data with probabilistic label of affordance related to the object. It contains 18 affordance labels across 23,000 objects from the partnet dataset. To detect affordances, we need to understand the local geometry, interpret semantic information, and probabilistic values to each point to determine the possible affordance on the object. To achieve this, we propose LGAffordNet, a local geometry affordance detection network. It consists of a series of semantic geometry correlator blocks and a class specific classifier. This architecture takes a point cloud with n points as inputs, where each point has 3 coordinates and provides 18 affordance probabilities as output for each point. The semantic geometric correlator is a block that includes local geometry descriptor for extracting local geometries and an edge convolution to capture the semantic information of the object. The local geometry descriptor combines several features such as edges between the query point and its two nearest neighbors, the edge length, the calculation of the normals, and the distribution of the points in the neighborhood. Specifically, Pi represents the query point, E1 and E2 represents the edge between the query point Pi and its nearest neighbors Pj1 and Pj2, respectively, describing the sparsity of the point cloud. The normal n is computed from E1 and E2, providing the information of the orientation of the local patch. The mean mu I and standard deviation sigma I of the points gives insight into the information of surface or curvature. These features provide critical information about the local surface geometry, which is essential for understanding the possible affordance for a point in the object. In similar fashion, we include three semantic geometric correlator blocks in series, which extracts the true semantics by understanding the neighborhood. We visualize the effect of semantic geometric correlator at each stage and compare with KNN. Notice the red point is the query point and the blue point are the local neighborhood considering the features. For KNN, the features are XYZ, and for S1, S2, and S3, the features are output of the semantic geometric correlator blocks which are considered in series. We infer that the semantic geometric correlator at each layer captures the semantics of the mug's handle and refines it over successive layers from S1 to S3. To predict the affordance on the object with the geometric features captured from the series of semantic geometric correlator blocks, we employ a class specific classifier. For an object, there can be multiple affordances at a point. For example, for a bag's handle, we can grab and lift the bag. To map one point to multiple affordance, we build an individual classifier for each affordance classes. This helps to capture specific information to each affordance class without unlearning features. With this setup, the full LGAffordNet architecture is trained on 3D AffordanceNet dataset. To fine-tune the weights, we calculate the loss between the predicted and the ground truth affordance. We use a combination of binary cross entropy and a dice loss. Binary cross entropy is used to handle the predictions of affordance and fine-tune the feature extraction module. A point cloud consists of both affordable and inhibited regions. Affordable regions are the areas where human interaction is feasible, while the inhibited regions are the areas where interaction is hindered. Typically, affordable regions constitute a smaller regions of the point cloud compared to inhibited regions. To address this imbalance, we employ dice loss, which helps to improve the accuracy of the affordance detection. Here we show some results on identified objects from the 3D AffordanceNet dataset. Here we compare our results with state-of-the-art methods on affordance detection. The state-of-the-art method refers to the modified DGCINN demonstrated in the 3D AffordanceNet paper. We can see a model detects the lift part, which is undetected in 3D AffordanceNet, as well as the open and the contain affordance are missing in 3D AffordanceNet model. Additionally, the grasp affordance is detected by LGAffordNet but is absent in the ground truth, as humans naturally grasp the bag in these areas. On headphones, we observe that the grasp part in LGAffordNet is accurate and has higher confidence than the SOTA and the ground truth, reflecting the actual grasp of a person on the headphones. The listen region also has a higher probability than the SOTA. On hat, we see that grasp part is detected with higher probability by LGAffordNet, which is missing in the ground truth. For a bag, the lift part is detected by LGAffordNet but is missing in the SOTA. Additionally, the contain part is well detected by LGAffordNet, which is absent in the ground truth. On bottle, the wrap grasp part is detected by LGAffordNet but is missing in the state-of-the-art method, along with the pore region, which has a higher probability. Overall, visual results are compared with SOTA and the ground truth. We perform quantitative comparison considering MIOU, MAP, MAUC, and MSC as evaluation metrics with SOTA method. We also examine the change in MIOU as it explains the actual prediction of the affordance compared with ground truth. We have computed the metrics for each affordance and their average. In average, we observe a 3.9% increase in MIOU compared to SOTA. Notably, pull and lay affordance have increased by 24.7 and 22.6 respectively. However, lift, wrap grasp, cut and step have decreased by 1.3, 1.4, 4.7 and 2.9 respectively. The main reason for the decrease in MIOE is certain affordances are not labeled in the ground truth, but the methods have detected them, as shown in the case of door, where the pull affordance is missing in the ground truth but detected by LGAffordNet. We can also see the keyboard region where the LGAffordNet has detected the press affordance, but in the ground truth the region is not labeled. This mislabeling affects the training of the architecture, resulting in lower MIOUs. Towards generalizability, we assess the effectiveness of LGAffordNet previously trained for affordance detection in an extended application for object classification. Here, we replace class specific classifier with a max pool and a linear classifier. We freeze the weights of semantic geometry correlator blocks and keep the further part for training the classification model. We compare the classification accuracy achieved by a model with state of the art methods which are trained on end to end for point cloud classification methods. It's important to note that the end to end trained models referenced in the comparison are trained directly on ModelNet 40 dataset, whereas LGAffordNet does not have information about the dataset. This comparison allows us to measure the adaptability and efficacy of the features learned by LGAffordNet for point cloud classification, demonstrating its potential utility in scenarios where data specific training data may be limited or unavailable. To conclude, we propose LGAffordNet, a local geometry aware affordance detection network for 3D point clouds. We demonstrate the results and compare them with SOTA qualitatively and quantitatively. We also discuss the challenges in the dataset that affect the model's detection. We also demonstrate the generalizability of LGAffordNet on classification. Thank you. For more information, contact us at savvy@kelitech.ac.in or visit us at savvy.co.in.